everyone, this is Babitha, working as Assistant Professor in the Department of ECE in Institute of Aeronautical Engineering. In this session, I'm going to discuss about op-amp comparator circuit as well as op-amp square wave generator. So these are the applications of the operational amplifier. So while coming to the contents, here I'm going to revise few points related to the operational amplifier. And while coming to the applications of the operational amplifier, I'm going to discuss about operational amplifier comparator circuit as well as operational amplifier square wave generator. So before going to the applications, first of all, we have to know why we are moving for the operational amplifier here. So generally, if we take the single stage amplifier circuit, it will amplify the applied input signal, okay, and across the output we will get the amplified version of the applied input signal. So this particular single stage amplifier can able to provide the different voltage gain, current gain, input impedance as well as output impedance. But these parameters provided by the single stage amplifier may not able to run the all practical applications. Okay, it cannot able to run all practical applications. So in order to overcome that only, again we went for the multi-stage amplifiers. So these multi-stage amplifiers we can able to implement by cascading the different single stage amplifiers here. We can take either 2 or more number of stages here so that we can able to improve the amplifier parameters. Those are nothing but voltage gain, current gain, input output impedance parameters we can improve in order to interconnect the different stages of the single stage amplifiers in the multi-stage amplifier. So how these parameters are increasing here means in the multi-stage amplifier, suppose I am taking 3 stages. So 3 stages means 3 single stage amplifiers we are cascading. That is nothing but output of the first stage we are connecting to the second stage, and the output of the second stage again we are connecting to the third stage. So the final output is the third stage output here. So if we take the overall voltage gain for this 3 stage multi-stage amplifier, that is the gain of the first stage and the gain of the second stage as well as the gain of the third stage. So how many number of stages we are increasing, that much amount of gain we can able to improve in the case of multi-stage amplifiers. So generally we'll prefer the 2-stage amplifiers only to increase these parameters, and some of the multi-stage amplifiers can able to improve some parameters. Suppose if we take the Darlington amplifier, it can able to improve the current gain. If we take the Cascode amplifier, it can able to improve the voltage gain. And if we take the only normal RC coupled amplifier with the CE amplifiers, that can able to amplify the voltage gain, or that can able to increase the level of the voltage gain along with the input resistance. So while coming to the amplifier parameters, these 3 should be high, these values should be high, this R0 should be low here to provide the proper amplification across the output. And this single stage amplifier can be able to amplify the low frequency signals, and this multi-stage amplifier can able to amplify the mid-frequency range of signals. But what about high frequency range of signals? So in order to amplify the all frequency range of signals, we are moving for the differential amplifier. So in the case of differential amplifier, to implement this, we are taking 2 identical transistors with the similar characteristics, and those 2 transistors should have same collector resistance as well as same emitter resistance, so that we can able to couple the 2 transistors to make it as the differential amplifier. So how we can able to couple the 2 transistors means by providing the common power supplies VCC as well as VEE to the collector and emitter terminals respectively. And for the two transistors, we are providing two different input voltages two input voltages, so that the basic function of this differential amplifier is to amplify the differential voltage whatever we are providing to the two inputs of the differential amplifier, that is V1 minus V2. V1 is the first transistor input and V2 is the second transistor input. So always differential amplifier will amplify the difference of these applied to input signals. So these differential amplifier will available in four configurations, that is dual in, balanced output, dual input, unbalanced output, single input, balanced output, and single input, unbalanced output. So here the construction and the analysis of all these four configurations are same, but the thing is these four can be differentiated by how many number of inputs we are providing to these amplifiers, whether we are providing two inputs to the two transistors or else whether we are providing single input to the only one transistor. If we are using the two inputs means those are dual input amplifiers. If we are using the single input means those are the single input amplifiers. And what about balanced and unbalanced here? Once we are measuring the output across the common point of two collector terminals of the differential amplifier, so that we can call it as balanced amplifier, or else if we measure across any one of the collector of the transistor, so that we can call it as the unbalanced differential amplifier. So why I am telling all these here means these first three configurations we are going to utilize in the operational amplifier to implement the operational amplifier. That dual input balanced output, dual input unbalanced, and single input balanced output differential amplifiers we are utilizing to design or to construct the operational amplifier. So what is the basic function of this operational amplifier? Along with the amplification, it can able to perform all the mathematical operations here, that is that may be the addition, subtraction, integration, differentiation, etc. So this can be able to amplify both the AC signals as well as DC signals, and it can able to provide very high gain. And this operational amplifier can able to amplify all frequency range of signals from low to high, that is from 0 to some megahertz. This is unlike to the single stage and multi-stage. Why? Because single stage amplifiers are restricted to the low frequency range of signals, and multi-stage amplifiers are restricted to the mid frequency range of signals. But operational amplifier can able to amplify all the range of signals. Even though multi-stage amplifier also can able to amplify all frequency range of signals, but in the mid frequency range only it can able to provide very high gain. Okay. And this operational amplifier we can utilize in the linear applications as well as in the non-linear applications to design linear circuits as well as non-linear circuits. Linear circuits means the output voltage or current will varies with respect to the applied input signal. In this linear applications, for example, I can say differentiator, integrator, adder, subtractor, all comes under linear applications. So while coming to the non-linear applications, we may get either comparison, comparator, and square wave generator, triangular wave generator, all comes under the non-linear applications. So in the previous sessions, we covered already linear applications of the operational amplifier in that op-amp differentiator as well as op-amp integrator. So in this session, I am going to discuss about the non-linear applications of the operational amplifier. So in that first application is the op-amp comparator. So we will discuss about operational amplifier comparator. So in order to utilize the operational amplifier for any practical applications, it should follow the two rules. So the first one is the input terminals of the op-amp should not draw or source any current whenever we are not providing any external voltage. That is nothing but whenever our differential input voltage to the operational amplifier is 0 means it should not draw or it should not source any current or voltage to the operational amplifier. And second condition is the output of the operational amplifier will do whatever it can to make the voltage difference between the two inputs is zero. That is nothing but Vd equal to V1 minus V2 to make it as this zero. To make it as this one zero means we need to apply V1 as well as V2 also zero. But in some cases, whenever if we apply both the input voltages are zero also, it is taking some differential voltage. But if we suppose if we are not nullifying this differential voltage whenever the input voltages are not present means it will provide the error across the output of the circuit. So that's why before designing the circuit or before operating the circuit, we have to see whether it is zero or not. If it is not zero, we have to make it as zero by applying the external voltage or by varying any parameters in the circuit. One of the nonlinear application of the operational amplifier is the comparator. So the basic function of the comparator is which compares the two inputs, whatever we are applying to the operational amplifier. So generally, the operational amplifier I have already mentioned, it is having two input terminals, that is inverting terminal and non-inverting terminal. Okay, and this one we are taking here it as V1 and V2, for example, and it requires two supplies plus VCC and minus VEE, and the output we will measure across here. Okay, so the function of the comparator is to whatever the voltages we are providing across the inverting terminal as well as non-inverting terminal, that is nothing but V1 and V2. So it will compare the two voltages. According to that, it will provide the output, whether which one is greater or which one is less. So this operational amplifier comparator is the non-linear type of the application. So here we are having two types of operational amplifier comparators. Those are inverting comparator and non-inverting comparator. So in that, first of all, I am moving for the inverting comparator. So how we can say it as inverting comparator means, so whatever the input signal we wanted to compare, that we are giving to the inverting terminal of the comparator circuit or else op-amp circuit, so that we can call it as the inverting comparator. But what about the other input terminal? Other input terminal should connect it to the reference voltage. So that is nothing but depending upon input signal for which terminal we are applying. According to that, we can say which type of comparator it is. So in this case, we are providing for the inverting terminal. So that's why it is called as inverting comparator. So this is the circuit for the inverting comparator. So to design this, I considered one operational amplifier. Okay, and for the inverting terminal, I am providing the input voltage Vi. So this particular input voltage Vi compared with the reference voltage connected to the non-inverting terminal, and this plus VCC and minus VE are the supply voltages required for this op-amp. And this is the 741 IC or operational amplifier, and this is the second pin of that IC, and this is third pin, this is fourth and 7, and this is sixth pin. Always across second and third pins we will provide the inputs, and across the sixth pin we will measure the output. Okay, so in this case I have already mentioned for the inverting terminal we are providing the input voltage, and across the non-inverting terminal we are providing the reference voltage. So this comparator is called as an inverting comparator because the input voltage which has to be compared is applied to the inverting terminal of the operational amplifier. Because of that reason we are calling it as the inverting comparator. So now we will see the operation of this inverting comparator. For that purpose, again I am considering the same circuit here. So in this case, we may get output voltage as either plus V saturation or minus V saturation. That is depends upon the input voltage as well as the reference voltage. Suppose if my input voltage Vi applied is greater than the reference voltage, That is nothing but here VI is negative value and V reference is the positive value. Why? Because VI is connected to the inverting terminal and V reference is connected to the non-inverting terminal. So in this case, what is my output voltage? V naught is equal to minus V saturation. I will get. Why? Because minus voltage is greater than the positive voltage. Negative voltage is greater than the positive voltage. So that's why my output for this particular condition is minus V saturation. And similarly, if my input voltage is, this is the first condition and this is second condition, whenever the input voltage is less than the reference voltage. So in this case also, here VI is the negative voltage and V reference is the positive voltage, but here the negative voltage is less than the positive voltage. There is nothing but positive voltage is more. So that's why the output is plus V saturation. So for this particular condition, I'll get this output. So always this inverting comparator will shift to the plus Vsat to minus Vsat and from minus Vsat to plus Vsat. So now we'll see one example related to this inverting comparator. So we'll draw waveform for the particular inverting comparator circuit whenever we are applying the sinusoidal input signal to that sinusoidal input signal to the inverting terminal of the operational amplifier and reference voltage is connected to the non-inverting terminal, and here I am considering the reference voltage as 0 here. So for that purpose, I am considering again the inverting comparator circuit. So for the inverting terminal, I am applying the sinusoidal signal. This is my Vin. Okay, and the reference voltage V reference. This is Vin and this is V reference voltage. I am taking here it as 0. So in this case, so we are applying the positive half cycle as well as negative half cycle of the input signal. So I am taking only the positive half cycle of the my input signal and V reference is 0. So during this positive half cycle of the sinusoidal signal, that is nothing but what during the positive half cycle means the voltage which is present at the inverting terminal of the operational amplifier is greater than the voltage which is present at the non-inverting terminal. That is nothing but V in is greater than V reference here. So, but my V in is connected to the inverting terminal here. So, that's why my output in this condition is minus V saturation. And similarly, if I take the negative half cycle, if I apply the negative half cycle to the inverting input of the operational amplifier. So during the negative half cycle, what will happen? This applied input voltage is less than the reference voltage. Why? Because it is in the negative value, but the reference voltage is 0. So it is less than the reference voltage. So the signal which is present at the inverting terminal of the op amp is less than the 0. So in this case, my output voltage is plus Vsat. Why? Because this one is higher compared to this one. So that's why the output is plus Vsat. That is nothing but during the positive half cycle, we will get the negative saturation, and during the negative half cycle, we are getting the positive saturation. So that I am showing in the form of waveforms. This is my input signal, that is the sinusoidal signal, and this is my output signal in the form of square wave we are getting here. And if you see this waveform, we can say during the positive half cycle we are getting the minus Vsat, and during the negative half cycle we are getting the positive V saturation. So this one will repeat for all the cycles. And in this case, output is changing its value whenever the input is crossing 0 volts. That is nothing but from here to here, the waveform is present here in the positive half cycle. From here to here, waveform is present, and after that it is moving to the negative half cycle, but before that it is crossing the zero axis here. Okay, it is crossing the 0 volts or zero axis here. So that because of that reason, this particular inverting comparator is also called as inverting zero crossing detector. Why? Because whenever the input voltage is crossing the 0 volts, there is a variation or change in the output signal or output voltage. So because of that reason, we can call it as the inverting zero crossing detector. And next type of comparator is the non-inverting comparator. So what is the basic difference between the inverting comparator as well as the non-inverting comparator? Here it is. In the case of inverting comparator, we provide the input signal to the inverting terminal. Similarly, in the case of non-inverting comparator, we need to provide the input signal to the non-inverting terminal here. And the reference voltage, we need to connect it to the negative terminal of the operational amplifier. So this is again, this is second pin, this is third pin, this is 7th and 4th and 6th pins of 741 operational amplifier. So I have already mentioned, whenever the input we are applying to the non-inverting terminal means non-inverting comparator, and it will compare both the reference voltage as well as the input voltage applied to the inverting as well as non-inverting terminals of the operational amplifier. So if you see the operation of this one, so in the output it may give either plus V saturation or minus V saturation, that is depends upon the applied input signal. So for example, in this case, if my input signal or Vi is greater than the reference voltage, okay, my applied input voltage is greater than the reference voltage, in that case my output signal is plus V saturation. Why it is plus V saturation means Vi is connected to the non-inverting terminal, positive. So this value is high compared to this negative value. So that's why the output is plus V saturation. And similarly, if my input voltage is less than the reference voltage, that is nothing but positive voltage is less than the negative voltage. So the negative voltage is only higher than the positive voltage. So in this particular case, my output is minus V saturation. So in the case of non-inverting comparator, it will always change from plus V sat to minus V sat and from minus V sat to plus V sat. So now we'll see one example related to this non-inverting comparator. So for that, I am considering the non-inverting comparator again. For the non-inverting terminal, I am applying the input signal as the sinusoidal signal. This is my Vi, and this reference voltage I am taking here it as 0, same as in the case of inverting comparator. So now we will see what is the output we can expect in this case. So in this case, during the positive half cycle of the Vi with respect to T. So only I am taking the positive half cycle from 0 to T by 2. So in this case, what will happen? This is 0 volts. V reference is 0 volts. So for the positive half cycle, what will happen? The input voltage is greater than the reference voltage, so that my output is plus V saturation. So output is plus V saturation. And similarly, if I take the negative half cycle of the input signal. So in the case of negative half cycle, what will happen? This Vi is less than the V reference voltage. Vi is less than the V reference voltage, that is nothing but this positive, for the positive terminal we are providing the negative voltage. Okay, so this is the negative value and this is the 0 value, but this negative value is less than this 0 value. So that's why what is the polarity is there that will appear across the output? That is nothing but my output is minus V saturation in this condition. So it is changing from plus V sat to minus V sat. So this is the input and output waveforms for the non-inverting comparator. See here. For the positive half cycle of the sinusoidal signal, we are getting the plus V sat. In the previous circuit, we got it is the negative, but here it is the positive. Why? Because it is the non-inverting operational amplifier. And for the negative half cycle, it is providing the negative signal only. So this particular circuit, we can call it as a non-inverting zero crossing detector. Why? Because in this case also, whenever the input signal is changing from positive direction to the negative direction, it is crossing the zero signal here. So that's why it is non-inverting zero crossing detector. Non-inverting comparator is also called as non-inverting zero crossing detector. So this is, we can call, whenever the reference voltage is zero only, we can call it as a zero crossing detector. But instead of the zero, if I take something 1 volt or 2 volts, means we cannot say it as a zero crossing detector. Why? Because the output will change once the input signal crosses that reference voltage only in that particular case. So that's why we cannot say whenever the reference voltage is something value present, means we cannot say it as the zero crossing detector. Once the reference voltage is zero only, we can call it as the zero crossing detector. That may be in the inverting case or in the non-inverting case. So next application of the operational amplifier is the square wave generator. So what is the operation what we discussed in the case of comparator that we are going to utilize in the case of square wave generator here. So what is mean by this square wave generator? It is the electronic circuit which is used to generate the square wave as the output here. Okay, so the circuit diagram of this square wave generator I am showing here. So in this particular circuit, I am going to utilize both the positive feedback as well as the negative feedback here. See, why I am using both the feedbacks here means this positive feedback is used to generate the waveform. Okay, this is used to generate the waveform. And this negative feedback is used to improve the input impedance. Okay, and it is reduces the noise and it reduces the disturbance and it improves the bandwidth of the circuit. So in order to take features of both the feedbacks, that's why we are utilizing both the feedbacks in the case of a square wave generator. So first we'll see the construction of the square wave generator. For that purpose, same circuit I am considering here. In this case, if we see this particular circuit, the resistance R1 from the output terminal 6 or V0 are connecting back to the inverting terminal of the operational amplifier. So we can say that this R1 resistance is providing the negative feedback to this operational amplifier or this square wave generator. And next, if we observe also, the resistance R2 is connected from output to the inverting terminal of the circuit, and this is connected to the inverting terminal and this is connected to the non-inverting terminal of the operational amplifier. So that we can say this R2 resistance is used to provide the positive feedback path to this square wave generator. And the capacitor C is connected to the inverting terminal of the operational amplifier, so that we can say the voltage which is developed across this capacitor is acts like an input for this inverting terminal of the circuit. And the one more component, that is R3, is connected to the non-inverting terminal of the operational amplifier. So the voltage which is present at this R3 is the input voltage to the non-inverting terminal of the operational amplifier. So for the inverting terminal, capacitor voltage as the input, and for the non-inverting terminal, the voltage across R3 acts like an input. But These R1, R2 are used to provide the negative and positive feedbacks respectively. So now we will see the operation of this circuit. For that purpose, again I am considering the same circuit here. So in this case, initially I am making the voltage across the capacitor VC as 0. Why it is 0 means we are not at all providing any signal, so that it cannot charge here. Okay, the capacitor will not charge initially. Why? Because we are not providing any input signal to this circuit. Okay, but there is some input offset voltage VIOS is present at the non-inverting terminal of the operational amplifier. So because of this offset voltage present at the non-inverting terminal, the output of this circuit will become plus Vsat. Why? Because it is connected to the non-inverting terminal. Okay, so once this output is plus Vsat means this capacitor will start charging through this resistance R1. Okay, the capacitor starts charging through this resistance R1. So once the capacitor starts charging means there is a voltage developing across the inverting terminal of the operational amplifier. That is nothing but negative voltage is becoming more compared to this positive voltage. So once the capacitor is fully charged with this plus V saturation, but it is connected to the inverting terminal, so that it will become the negative. So now this negative voltage is greater than this positive voltage present in the non-inverting terminal. So in this case, what will happen? My output voltage changes to minus Vsat. Why? Because this voltage is higher compared to this voltage. Okay, and again once this output is changed to minus Vsat means the capacitor again starts discharging through this resistance R1. Capacitor again starts discharging here. So once the capacitor again starts discharging means the voltage which is present in this inverting terminal will be reduces. So now this voltage is less. The voltage which is present in the inverting terminal is less compared to the positive terminal or non-inverting terminal. So in that case again it will change to the plus Vsat here. Okay, so in this way the circuit can able to change from plus Vsat to minus Vsat and minus Vsat to plus Vsat and again from plus Vsat to minus Vsat, depends upon the charging and discharging levels of the capacitor here. So this is the output signal we will get from that particular square wave circuit. So this is the case we will get whenever the voltage across R3 is greater than the voltage across the capacitor, that is at the inverting terminal. In that case we will get this particular output, and whenever the voltage across the capacitor is greater than the voltage which is present at the non-inverting terminal is VR3. If this capacitor voltage is greater than this one means we will get it as the negative saturation output. So from this square wave signal we can observe it is changing from plus Vsat to minus Vsat. And in this case output will be remains at one particular value for some duration, and after that it will transition to the another value, and again it will stay and it will be remain in that particular condition for some duration. That is nothing but during this particular duration from here to here it is in the plus saturation level, and from here to here it is in the negative saturation level of the output. So in this way the square wave generator can able to generate the square wave signal. So this square wave generator using operational amplifier, we can also call it as a stable multivibrator. Why we can call it as the stable multivibrator means the function of the stable multivibrator is to generate the square wave of required or desired frequency here. So here this plus V saturation and minus V saturation, that is square wave signal, indicates the output signal, and this charging, rising and falling of the waveforms indicates the capacitor voltage VC. So here VUT is nothing but the upper threshold voltage, VLT is nothing but the lower threshold voltage here. So this particular circuit is similar to the comparator with hysteresis or schematic trigger, except that the input voltage is replaced by a capacitor voltage here. Instead of input voltage, we are replacing the capacitor voltage. If we are replacing it with the input voltage, means it will become the comparator circuit. So this circuit has time dependent elements. Those are the resistances as well as capacitors. Resistance, which is present in the negative feedback, in the positive feedback, and the capacitor, which is present in the negative feedback. So these resistor and capacitors are used to set the desired frequency of the circuit. Then only it can able to generate the desired frequency range of signal. So what is the frequency of oscillation here? At what frequency range this particular square wave generator can able to generate the signal? So this frequency of oscillation we can determine from the capacitor voltage, that is changing from upper threshold voltage VUT and lower threshold voltage VLT. So depends upon this, the capacitor voltage is varying, and depends upon that we can able to determine the capacitance. And the voltage across this capacitor as a function of time, and it is given as Vc of t here. So this Vc of t is the instantaneous voltage across the capacitor. So what is mean by this instantaneous voltage? So whenever the input offset voltage which is applied to the operational amplifier, because of that voltage we are getting the output in the operational amplifier, and because of that output voltage only this capacitor is going to charge. So because of that applied output voltage, it is charging here. That voltage we are calling it as the instantaneous voltage. And along with this, we are also considering the V initial voltage. That is the initial voltage of the circuit. And we are also taking the V maximum voltage. That is the V maximum is nothing but the maximum charging voltage of the capacitor, or maximum voltage of the capacitor. So, in order to determine the total time required for one oscillation is given as the frequency of oscillation, and that can be determined from F naught equal to 1 by T here. So, T is nothing but the time required for one particular oscillation. Okay, time required for one particular oscillation. So, in this particular square wave generator circuit, the frequency of oscillation in terms of resistance and capacitance, and in terms of capacitor voltage levels, as well as in terms of output signal voltage levels, we can write it as 1 by 2 RFC. These will determine the frequency of oscillation, and this plus Vsat minus VLT is nothing but output voltage minus the capacitor voltage divided by output voltage minus capacitor discharging voltage here. VLT is the lower threshold voltage and VUT is the upper threshold voltage. So by using this particular formula, we can able to determine the frequency of generating output signal. That is nothing but frequency of the square wave signal. This square wave generator falls under the non-linear application of the operational amplifier. So that's why output is not varying linearly with respect to the applied input signal here. Because of that reason, we are calling it as the non-linear application of the operational amplifier. So in the non-linear application, one more application is also there, that is the triangular wave generator. For the square wave generator, if we interconnect one integrator circuit, we can able to generate the triangular wave generator. So both the both the square wave circuit as well as integrator circuit are designed with the operational amplifier only. Then only we can able to generate the op-amp based triangular wave generator. From that we can able to generate the triangular wave as the output here. So in this session we have discussed, we revised the what is meant by operational amplifier and inverting comparator related example as well as non-inverting comparator related example, and that same concept we applied in the square wave generator to generate the square wave signal. So this particular square wave signal we can utilize for the practical applications in order to see the performance of particular circuit. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.